Modern scientific publishing is choking on friction. Every year, researchers generate petabytes of high-value data, only to have it stall in a chaotic mess of unformatted text drafts and fragmented manual citation rules. The heaviest lift for bioinformaticians rarely happens during the experiment. Synthesizing hundreds of prior papers and bending raw data to fit rigid publication standards consumes more time than the actual laboratory work. OMNIBIOFEX AI 2.0 operates as an autonomous multi-agent orchestration engine, purpose-built for high-impact academic output. To scale research volume, the human must be removed from the formatting loop. The researcher inputs the hypothesis. The system handles the document structure. Unlike standard large language models that predict the next token in a vacuum, a multi-agent swarm divides the workload across specialized nodes to construct a document mathematically. This architecture is powered by the 70 billion parameter Llama 3.3 open weights model. We coupled this engine with a micro-transactional compute system that allocates processing resources strictly on demand. This split screen compares the drafting workflows. On the left, manual drafting is an erratic, iterative loop of revisions and formatting corrections. On the right, the multi-agent pipeline is linear and deterministic, snapping distinct components into place. Producing documents that meet peer-reviewed standards requires an architecture built on absolute operational constraints. The computational core of OMNIBIOFEX is Llama 3.3 70B, giving the system the capacity for doctoral-level reasoning. When complex biochemical pathways are generated purely from latent model weights, the risk of hallucination is unacceptably high for academic use. The structural solution to this problem is the model's 128,000 token context window. This diagram illustrates context injection. Instead of relying on internal memory, users feed reference URLs directly into this wide intake pipe. As these verified data nodes flow through, they physically restrict the model's knowledge base. The semantic synthesis is locked to the provided prior research. Operating within this localized context, the engine can synthesize hundreds of papers to execute literature reviews and identify research gaps. By grounding the 70 billion parameter engine in verified data boundaries, the system aligns its output with a technical synthesis rigor of 0.99. The process begins in a Gemini-style interface. The researcher sets exact specifications, enforcing the document length, up to a 4,000-word expert report, and locking in the academic tone. Submitting the prompt triggers this workflow topology. The central node delegates tasks to 3 distinct agent paths simultaneously. Here, the bibliographer agent cross-references the injected URLs, mapping the web sources directly to embedded citation brackets. At the same time, the methodologist agent takes the raw synthesized data and stacks it into rigid, labeled academic sections, separating the abstract from the methodology and results. Dividing these formatting tasks across specialized agents allows the engine to output massive documents without the logic degradation typical of standard large language models. Once synthesis is complete, the swarm delivers the final document to a read-only environment, the locked canvas. Standard AI platforms use static templates that eventually fail because language models drift off format as the generation lengthens. OMNIBIOFEX enforces strict visual constraints. On the canvas, the paper adheres to Weight 900 grotesque typography, formatted entirely in solid black, with omni-green impact headings. The canvas itself is locked. This physically blocks the user from accidentally deleting citations or degrading the document's structural integrity. To make localized revisions, users highlight the specific text, type instructions into the sidebar, and apply targeted micro-edits. This workflow relies on a micro-transactional compute model, abandoning monthly subscription tiers. Generating a full autonomous multi-agent document costs exactly 1 base credit, or 9 rupees. For revisions, the system uses a double decimal tracking architecture to calculate server costs instantly. Contextual edits track directly to the highlighted text, costing 0.0012 credits per word. You only pay for the specific words generated during a revision. Decoupling generation from subscriptions creates a deterministic economic model. Your compute expenditure maps to your scientific output. This structured output extends past academic publishing into Mode 03 and Mode 04 commercialization outputs. This horizontal timeline maps how a single set of raw research data splits into 2 parallel tracks. The same engine that performs academic gap analysis on the top track generates B2B API licensing models on the bottom track. The AI analyzes market feasibility directly from the scientific data and maps out the features required for a minimum viable product. It then automatically outlines a complete 12-slide Series A investor pitch deck based on the user's specific laboratory expertise. Maintaining strict structural rigor across all modes creates a cost-deterministic bridge between the laboratory and venture capital. Processing unreleased research data requires absolute security to prevent intellectual property theft and model scraping. All generated content is synced to the Firebase Cloud Vault via isolated, secure pathways. Furthermore, the LLM nodes operate on a strictly stateless architecture. Once the document is formatted, the connection to external nodes severs, wiping their memory cache. With the data secured in the vault, the user executes a one-click export, compiling the document into PDF, Word, or raw LaTeX formats. True data ownership is achieved only when the processing engine forgets the scientific hypothesis the moment the export is finalized. From synthesizing a raw hypothesis with a 128K context window to outputting a formatted LaTeX document, OMNIBIOFEX enforces precision. The multi-agent swarm completely removes the friction of formatting, locking abstract academic concepts into a standardized, structurally rigid format. Generating this output consumes non-recoverable API compute power and server resources instantly, which is why the platform enforces a strict no-refund policy. The future of scientific acceleration relies on rigorously constrained AI systems, engines that respect the researcher's data, enforce structural integrity, and optimize compute economics.